summary of results. This is a fairly brief summary I'm going to go through. I think from my perspective, the two talks I gave yesterday plus this last one are the most important of the 5 talks I'm giving. I've titled this Asteroid Lunar Occultation Results for 2014 and 15. In fact, there's no lunar occultations in this report, so let's move on to the next slide. Here's a plot of the number of occultation events we observe each year. It's been over 200 now since Hipparchus, since UCAC4 became available. It's 2008. Well, 2008 was probably UCAC2. But it's been sort of consistent. We had a drop down in 2012 and 13, but picked up again. I would like to think that in years to come, those numbers will increase significantly because we have greater certainty about the events we actually observing. Next slide. Here's, oh, geez, my background screen on this is not very suitable. Number of successful events by region and the maximum number of sites in an event. And this is for the calendar year 2015. In Australasia, that's Australia and New Zealand, and might have been an island somewhere around here as well. 44 events, maximum number of sites with, for any of those events was 16 sites. And given the population, low population density of Australia, I reckon that's pretty good for you. Europe, 61 events, and they had an event with 50 sites. Japan, need to keep in mind that Japan is a fairly narrow string of islands, high density, but not a very large country. 25 events with 17 sites. And the United States, or I say US, but it's really North America. Canada's included in that. Canada and not sure whether Mexico, if there's anything from there, but anyway, 88 events from 20, and with maximum number of sites for event was 27. Next slide. We get double stars discovered in asteroidal occultations. Separations are typically 0.1 to 0.001 seconds arc. That's 1 to 100 milliarc seconds. If there are several observers, we can do a proper double star solution, and the uncertainty in the separation can be significantly less than a milliarc second. Next slide. Five double stars discovered since January 2014. The writing on this is not very large. See, the first event, separation 1.2 milliarc seconds. The second one's 3 milliarc seconds. The third is 30 milliarc seconds. Then 42 and 41 milliarc seconds. Yeah, just keep in mind, I spoke about Gaia yesterday. The first 3 of those stars are below the resolution of Gaia. Our occultation, asteroidal occultation results, and our lunar occultation results will produce double star discoveries which are beyond the capabilities of Gaia. Next slide. And this is just a sample of 8 examples of good profiles fitted to shape models. 2014, September 6, good fit to a convex. I should say I put this presentation together a couple of months ago before I got involved with the proper shape model determination. So I've done no fitting by rotational adjustment in these slides. Next slide. Elk mean, 4 chords, very nice fit. Again, no rotational fit applied to that, but it's a good fit to that shape model. And again, when you've got a fit to a shape model, then you've got a scale. Next one. Here's one which was a nice fit to the butt end of an asteroid with a whole heap of miss events. Gaia, we should not have this type of situation. We should have everybody getting the asteroid. Next slide. This is going to be a very short presentation. This was an interesting one. I forget whether this was observed in the US or the States. But it was a double occultation. The binary asteroid 90 Antiope occulted a star which turned out to be a double star. So the double star solution, here's this plot shows the double star solution looking at each component of the asteroid separately. And there's significant differences there, which has got relatively low number of chords and parameters about the shape of the asteroid. But you can see the type of uncertainties that you can get out of it. And the next slide. Next slide. That shows the 2 components of the asteroids and all the observers. And there's four observers were between the 2 components. I think there was a suggestion from, I forget where it was it somebody in Europe or whether it's from America suggesting that there's a club of people who have been located between the 2 components of a double asteroid, and I think there's about 6 people in that club now. Don't know if anyone at the meeting would claim to be a member of that club. A bit of an interesting sideline. Next slide. And here's Tony George is the Pillars of Hercules Club. Anyway, this one shows fits to 2 different shape models for 2 occultations of 409 Aspasia. The right-hand models are concave shape models. They're a more complex shape model, allows for dips and valleys as well as just mountains. And interestingly, the convex models on the left provide a better fit than the concave models on the right. And they've still got lots of development stuff to do on the shape model area, but they're getting really good results. And next slide, we must be getting. Oh, 275 Sapientia. I forget where that was observed, but you can see a large number of chords, and we don't have a shape model for that at the moment. But that's possible. I would like to think in years to come that type of chord coverage will be the norm once we have reliable path prediction, so we know that yes, we'll drive 233 kilometres tonight to go and observe an event at this point in the countryside with a total confidence of getting the event, rather than going somewhere on a wing and a prayer. Next slide. Amphitrite. Here's an interesting case of an old shape model, and then they published an updated shape model based on a reanalysis of light curves, and the updated shape model fits the occultation light curves rather nicely. So there's a bit of interaction between the shape models and the occultation data. We're developing a good relationship with Joseph Jurek, who's behind Dammit, and we will be going the same path with the ISAM site as well. Next slide, which is the last effective slide. UTERP, only 4 chords on that, but again, you can see that fits that shape model quite nicely. And that's an illustration of if you have an indication on the shape model of the scale used to draw that shape model, then our occultation diameters chords give you a very definite scale for the asteroid. And that's it for that presentation. Questions? Derek's asking, will occultation results end up pointing to any errors in Gaia's position? I don't expect that's going to be the case. My understanding is that they are doing astrometry of Gaia every night somewhere in Europe or the Canaries to tie its position down accurately. And the Europeans are deadly serious about Gaia, and my understanding is its performance is exceeding their basic expectations. We'll wait and see, I guess. But our occultation results will depend on Gaia, but will not. I don't expect to find any flaws in Gaia out of it. Special pre-release issue of the Gaia position for the one particular star. I don't know what hoops they had to jump through to get it released, but it was released on the justification of it being an occultation of Pluto and the possibilities of getting the central flash phenomena. And there was at least 10 people recorded the occultation, and the offset from the prediction was less than 10 milliarc seconds from memory. The process of using Gaia is looking good. Tony's recently analysed one of the light curves to one of the Pluto observers. Yes, it's the scene. Where we're heading to with this occultation stuff. I like to think of it the last 30 odd years, 30 years, 40 years, 30 years anyway that we've been doing this really is setting the groundwork for what we're going to be doing as from the end of September, once we have Gaia stuff available. I'm hoping to have the replacement for the Tycho 2 catalogue, the Tycho Gaia catalogue, out and distributed by the end of September, or in fact well before the end of September. So we should have Gaia star positions for our brighter events within 2 months, and Gaia positions with UCAC4 based derived proper motions. I would hope that will be operational sometime in October.